Hello, everybody. Welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. And every week, we'll have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
So this week, we have a special session with two speakers doing some amazing work touching on geometry. And our opener, Congyue, is going to talk about vector neurons, a general framework for SO3 equivariant networks. And our headliner, Lachlan, currently a PhD student in the Department of Modern Culture and Media at Brown University, and also a research fellow at Forensic Architecture, will give us a talk on how can we make geometry research practical in documentary journalism. And if you have any questions, please leave comments in the YouTube chat or our Discord channel. First, it is my pleasure to introduce our opener, Congyue Deng. She is a second-year PhD student in computer science at Stanford University, advised by Leonidas Guilbas. She's interested broadly in computer graphics, computer vision, and geometric computing. And more specifically, she's interested in developing and leveraging better data representations in 3D shape analysis and processing. And without further ado, I will give the stage to Congyue to talk about vector neurons.
Thanks for the introduction. It's my honor to be here, to be the opener. And I'll share my screen right now. Cool. So hi everyone, I'm Congyue Deng from Stanford University. Today I'm going to talk about my paper, Vector Neurons, a general framework for SO3 equivariant networks. A little bit background and intuitions. Why do we need equivariance or invariance in 3D data processing? So basically, traditional networks trained on aligned data sets, it's hard for them to generalize to unseen shapes. However, actually, this is not a hard task for human beings. Some psychology theory says that in human perception, there's this notion of invariance, which says no matter how different poses for different rotations, transformations the shape is at, you can always identify it as the same shape. So for neural networks, it's actually not an easy task. Like in current days, many neural networks, especially 3D neural networks, they're trained on aligned data, which means it's hard for them to generalize to unseen poses. Even sometimes, like you can apply data augmentation at the train time, say like adding random rotations to the data input to the network, but this is like decreasing your data efficiency, and you may need to train your network this longer time or like longer with more memory. So to alleviate all these issues, like people are trying to develop rotation equivariant or invariant networks in the 3D data processing field. Here, like I'm mentioning rotation more than say like general transformations. This is because like for translations, it's easier to cancel it out by just like centering the shape at the origin. But for the rotation, because the topology of the group itself is more complex, it's hard to just like say like doing something like just like centering it or like canceling it. So more concretely, the definition of equivariance and invariance here is that say like you want your for invariance, it's like no matter how you rotate your inputs, you want your network output to be always the same value. And for equivariance is that no matter what rotation you have at the input, you want your output to always rotate by that certain degree. And more concretely here, like for classification and also like segmentation in some data representation, it's invariance. And for reconstruction, it's equivariance. So here's what we are looking for in building the networks. And now here in our work, we propose vector neurons, which is a general framework or a toolbox for building a couple of network layers that are rotation equivariant. And with all these layers, you can build more complex network structures. And specifically, you can use this layer to build the same architecture as the classical point cloud networks to make the existing architectures equivariant. And it's overall, it's a simple and versatile framework. Let me start by introducing the representation itself. So classical neural networks, they're using these neuron connections between scalars where in other words, like each neuron in the network is a scalar feature, and with a couple of neurons stacked together, you get a latent feature of size C by 1, representing an activation of the network. However, it's hard here to actually see the group action of SO3 in such a latent representation. So instead, to really realize the SO3 representation in the latent spaces, we instead extend each neuron into a 3D vector, so resulting in the C by 3 latent activations as a network feature. As shown here, say like the network that now becomes a couple of connections between these vector neurons. More concretely, for point clouds, traditional networks here have like n by C by 3 features, where n is a number of points. But here, for our representation, we're representing the features as like n by C by 3 as the per point features. I'm mentioning this here because this may be a little bit confusing because the n dimension is unordered, but the c dimension is ordered, because n is representing the point set, but c is the ordered vector list features. Cool, and then with all these representations, it's quite straightforward to define the linear layer, where you still multiply weight matrices to the C by 3 vector list feature, and you get similar things like linear combinations at the output. But however, here you can also multiply the SO3 rotation matrix from the other side at any time. This results in the because these two operations are commutative, so like this is rotation equivariant. Also, one note here is that there's no bias term here because adding a bias term breaks equivariance. And actually, the linear layer is a bit trivial, but what's really non-trivial is the nonlinearities, because like we need to define nonlinear functions to the vector features. So here we are imitating the ReLU nonlinearity in classical neural networks. Recall that in classical neural network, what you're doing with ReLU is that you keep things that are greater than 0 unchanged, and what's below 0, you clip them to 0. So here we do something similar, but instead we first learn a data-dependent direction k from the input vectorless feature, and then with respect to k, you can define a plane. And what's above the plane, you keep it unchanged. What's below the plane, you clip it to the plane. Also, we need to define pooling operators, either for global pooling or for local poolings. What's easy to define is mean pooling, because taking average doesn't break anything about the vectors. However, for max pooling, it's a little bit more tricky. So what we are doing here is that, again, similar to the nonlinearity, we first learn data-dependent direction case, and then we compute the inner product or the projection of the vector features to that direction k, and take the arcmax along that direction, which is saying that we want to keep the signals that are strongest along these learnable directions. Also, we define normalizations that are essential to the performance of neural networks. Here, layer norm, instance norm, and also even dropout are quite easy to define, because like you're just like acting all the vector lists directly. But for batch normalization, it's a bit tricky. Although you can still define it directly as the other normalizations, but what the issue here is that because now we're assuming having random rotations at the input data, so averaging across all these arbitrary rotations, even at the latent space, will cancel out all your poses, which may give you something like standard at the origin. So instead, for batch normalization, instead of doing them directly to the features, we first take the element-wise 2 norms to the vectorless features, resulting in C by 1 norm featureless, and then do normalization on these features. Finally, we also define this invariant layer, because for a specific task as shown before, we need invariant outputs instead of the equivariant outputs. So here, the key idea here is that the inner product between two vectorless features are the inner product between two equivariant features are essentially invariant. A special case is that if you keep one of the features to be same as the input and the other feature to be of shape 3 by 3, this is just the canonicalization, where you're estimating a 3D frame from the input and canonicalize the 3D input. Also, in practice, in our implementation, we also concatenate the global feature, the global mean to the per point features, and then compute the per point canonicalization. This is because we want the network to be more aware of the global information. Otherwise, you're losing too much information through just dealing with per point features. Finally, we also show some network examples with all these layers. Like you can easily plug such representation in PointNet, where you just modify the per point features from scalar features to vectorless features, or you can also plug it into the message passing process into DGCN, resulting in this vector neuron version DGCN graph neural nets. And finally, we show some interesting results with the modifications. First is the classification. Here is the vector neural networks. You can see it's quite coherent across different rotations. Especially like at the second column is a generalization to unseen poses. Even at such a scenario, the vector neuron can easily like identify the objects. Also, even at the third column, the standard data augmentation, you can see that even under such a scenario, equivariance by construction works better than augmentation. Also, we have this neural implicit reconstruction where there are more visualizations that are fun. So here, like the third column with the data augmentation, you can see that even under such a scenario, your network has seen different poses at the train time. The traditional networks, they cannot easily reconstruct the shapes at unseen poses, but for vector neuron, for the equivariance by construction, you can easily get coherent outputs at different poses. Here are more examples. You can see the vanilla network sometimes give you blurry outputs at the random rotations, where sometimes they will average the shape features, and sometimes like this one is interesting. Like they will even have like false shape fires. Like here is the car cusp is identifying this as a chair. So that's a brief summary here. We propose vector neurons, a versatile framework for SO3 equivariant networks. Within this framework, we have a couple of building blocks like the linear layer, nonlinearities, pooling, normalization, and also the invariant layer. And finally, we show how it works on multiple tasks, especially the reconstruction results are quite interesting. And that's it. Thank you.
Thank you, Congyue, for the great talk. We will proceed to the talk of our headliner and have a joint Q&A session at the end. So now I introduce our headliner, Lachlan Kermode. He is a PhD student in the Department of Modern Culture and Media at Brown, and a research fellow at the research agency Forensic Architecture, which is a multidisciplinary research group based at Goldsmiths, University of London, that uses architectural techniques and technologies to investigate cases of state violence and the violations of human rights around the world. And after receiving an undergrad degree in computer science from Princeton University in 2018, he worked for several years as a software researcher at Forensic Architecture, and also as a software engineer building cloud infrastructure for machine learning models. He has also worked as a mobile developer and as a full stack engineer. Equipped with a technical background, he is currently interested in studying the political potential of open source and open hardware cultures, the history of computer science and software engineering as disciplinary practices, and the implications and the impacts of computing in media at large. So now I will give the stage to Lachlan.
Thanks so much, Lena, and thank you to the Toronto Geometry Colloquium for giving me the opportunity to speak about some of my work. So to get started, I just want to play one of our videos, which is about 12 minutes long, and hopefully it will serve as a good starting point for the kind of research that we do at Forensic Architecture. So I'll just share my screen here, and let me know if the sound is not working, but hopefully it will.
Shortly after 6 p.m. on August the 4th, an explosion ripped through the port of Beirut. It killed more than 200 people, wounded over 6,500, and destroyed large parts of the city. Forensic Architecture was invited by Madame Mass to examine open source information, including videos, photographs, and documents, to provide a timeline and a precise 3D model to help investigate the events of August the 4th. The model is available via this link. The first photograph of the warehouse on fire was uploaded to Twitter at 5:54 PM. We carefully geolocated this photograph by identifying the key buildings and calculated the camera's cone of vision. Of the smoke plume at the northeast corner of warehouse 12. Smoke plumes are continuously transforming and have a unique shape at every moment. We modelled the plume at this crucial stage to help synchronize other videos without a timestamp. A video shot at around the same time from one of the balconies of the residential tower building shows the same source of fire clearly on the same side of the warehouse. The shape of the plume and the heat source suggests that the fire had evolved. Another video, starting at 5:58 PM from the nearby St. George Hospital, provides 10 minutes of uninterrupted footage of the warehouse. Within 2 minutes, the smoke thickens and its colour changes to a darker shade. According to Gareth Collett, a UN explosives analyst we consulted, this suggests that the material burning inside the warehouse has changed. At 6:07 PM, a new intense heat source appears on the other, northwestern side of the warehouse, here, followed by a different, larger plume. The sparks that follow suggest the presence of small explosive charges, such as fireworks. 35 seconds later, at 6:08 PM, a large spherical plume appears above the centre of the warehouse. According to the explosives analyst, the symmetrical shape of the sphere suggests that it's a single point explosion originating in one particular place within the warehouse, and it's possible that as little as half of the 2,750 sacks of ammonium nitrate stored inside detonated. We use the shape of the two plumes from these explosions as metadata to synchronise the remaining footage. This video, taken from further back, provides an uninterrupted view of the events that followed. Within the span of 9 seconds, the spherical plume projected high into the atmosphere. Several tons of particulates thicken the air, and a red-coloured plume, 755 metres high, rose over the warehouse. We have thus identified 4 types of smoke plumes emanating from different parts of the warehouse within the space of these 14 minutes. The first plume, at 5:54 PM, emanates from the northeast corner of the warehouse. The second plume, at 6 PM, is from the same source point but has a darker colour. The third plume appears on the northwest side of the warehouse at 6:07 PM. The final plume is developed from a spherical explosion located at the centre of the warehouse at 6:08 PM. Each of these smoke plumes, with their distinct shape and colour, provide indications as to the arrangement of goods in the warehouse, the way the fire developed, and the layout of what was stored inside. A close-up examination helps in understanding the evolution of fire inside the warehouse. Early footage shows smoke leaking out of every opening, including the windows and the ceiling vents. From this point, at about 5:56 PM, the temperature inside the warehouse started rising rapidly. The smoke is visible as it changes colour to a darker shade, in this footage, from the east side. We stabilised the footage to reveal the full extent of the warehouse. The sounds of fireworks starts being heard at approximately 5:59 PM. It shows that many windows and doors are shut. According to the expert, confinement creates hotspots, areas of high temperature in which ammonium nitrate can get close to its combustion point. As reported by media outlets, the fire brigade arrived approximately 4 minutes after an initial call was made to the station at 5:54 p.m. In this footage, taken by the fire brigade on their arrival to the scene, the sound of fireworks continues to be heard. The 2,750 tons of ammonium nitrate were unloaded to this hangar in October 2014. And, as early as December of that year, various port and customs officials warned of the dangers posed by its storage. Many subsequent warnings were issued. In February 2015, for example, a chemical forensics expert commissioned by the Lebanese courts to report on the state of the stored ammonium nitrate described that 70% of the sacks were torn open, their contents spilling out, and some of the crystals had darkened. Leaked images from February 2020 indicate that the storage conditions had not improved. The sacks were still torn open and their contents were still spilling out. The bay numbers visible in the ceiling allowed us to locate these bags in bay 9 and 10. The images show the presence of a container and a stack of wooden pallets. Another video, taken on December the 18th, released by news outlet Al Jadid, shows the state of ammonium nitrate bags stored at bay 6 and surrounding door 9. Stacked ammonium nitrate bags are blocking the entrance. Here, we can see the numbers for bays 4 and 5. On the right of the videographer, between door 9 and 10, a white coloured wall is visible, suggesting the presence of a small service room. Together, these videos and images allowed us to map a total of 243 bags of ammonium nitrate in the space. Given the location of the source of the spherical plume, here at bay 8, the remaining 2,507 bags of ammonium nitrate should have been stored here, occupying almost 2,000 meters squared of space. But given the haphazard way the visible bags are stored, the space the entire stockpile occupied was likely larger. News reports suggest that in addition to the ammonium nitrate, the warehouse also stored 23 tons of fireworks, 50 tons of ammonium phosphate, 5 tons of tea and coffee, 5 rolls of slow-burning detonating cord, and 1,000 car tyres. Each of these materials burns differently. The combustion of tyres, for example, produces a dark and thick plume. According to the explosives expert, it could correspond to the dark plume we had located on the northeast corner of the warehouse, so we placed the tyres roughly here. The expert also told us that the white plume that appeared on the northwest of the warehouse corresponds to the ignition of fireworks. We therefore placed the fireworks roughly in this corner. From an engineering perspective, this is the spatial layout of a makeshift bomb, on the scale of a warehouse, awaiting detonation. According to Gareth Collett, ammonium nitrate is extremely difficult to detonate by fire alone. However, when confined and contaminated, this can lead to catastrophic detonation. It is sensitized by the presence of even the smallest quantity of additives, and hence should be separated. We reviewed international standards for the storage of ammonium nitrate. Internationally accepted benchmarks include British regulations. According to British standards, stacks of ammonium nitrate must be limited to 300 tons, and each stack must be at least 1 metre away from walls and other stacks. Australian standards are more stringent. Bags must be arranged in 500-ton stacks, but should be stored 890 metres away from the closest residential buildings. Using their equation to calculate safe distances, we can determine that a 2,750 stack of ammonium nitrate should have been stored 1,570 meters away from the closest residential building. NASA's damage map illustrates the extent of the blast. All these regulations prohibit the storage of combustible or explosive materials such as tires or fireworks in proximity to ammonium nitrate. This fact highlights the substantial and sustained state negligence which led to the formulation of a makeshift bomb. Around 1,000 of the survivors and victims' families have called for an independent investigation and public access to all relevant documents. As the search for political and economic accountability for the explosion of August 4th continues, Forensic Architecture and Madame Mass are making the model, the geolocated videos, and the source material used in the research publicly available via this link.
Great. So hopefully that gives you a clear idea of what the research agency that I work with, Forensic Architecture, does and is about. That was an investigation that we did relatively quickly compared to some of our other investigations, but it details some of the techniques that we're interested in and also the kind of basic principle of the organization, which is to do documentary journalism through architecture. So my name is Lachlan Kermode. As Selena mentioned, I'm a research fellow at Forensic Architecture. Forensic Architecture is an organization that is based at Goldsmiths University in London, and it's an academic research agency. So it was founded by the British-Israeli architect Eyal Weizman, and the mandate is to develop new techniques for investigating human rights violations using public domain, or as that kind of media is known in the journalistic world, open source media. So this is images from online that's publicly available, as you saw in that investigation that I just showed. The purpose of this work is to show it in courts of law. So these are typically international courts where human rights violations are being prosecuted, but we also disseminate our work as documentary journalism in a more general sense. So we're looking to detail what has happened for a general public in the same way that journalists are interested in doing. We also showcase our work in gallery spaces, so artistic gallery spaces. And the intention here is to interrupt the kind of white cube apolitical discourse that sometimes still unfortunately circulates in art, and turn the art gallery into a space where we can discuss things that matter, like the content of our investigations. We also publish selections of our work academically, and we make our tools and our method, as you saw in that investigation, publicly available, following the principles and practice generally of open science. So sometimes we make our models available on GitHub, other times we publish documents detailing the method. It depends on the investigation and the methods involved. Because we work almost exclusively with public domain or open source images, it means that we're typically dealing with low resolution images, not high resolution images that can be expected in certain industrial or media settings in other cases. Because of our academic mandate as well, like many of you, we gravitate towards cases that have hard problem domains. So we're a small research agency, and our goal is not to manufacture one process and apply that process indiscriminately to all possible human rights cases where that investigative technique can be useful, but instead we aim to find cases where it's unclear what method will be successful and work to find one in this kind of academic mode. In other words, our investigations typically take place in media contexts where reconstructing what has happened is not a simple technical task. The complications here could be for a number of reasons, and this is kind of what I want to talk about in this talk. I want to give you all an overview of what forensic architecture is, what we do, but also what the kinds of problem spaces that we encounter are, and how 3D research is a very contingent domain that is very interesting to us. So one major problem that we come up against is this, that algorithmic techniques that operate over images or video, this is a broad generalization, but it's certainly come up in our work, often assume that the media or the images that you're working with are of high fidelity. So reconstructive methods assume that you're working with high fidelity images. As I mentioned before, we're almost exclusively not working with high fidelity images, or we're very lucky if we find these high fidelity images or video. These images and video are often shot on smartphones and or under duress. And so they're not only kind of low quality in a technical sense, but also are not very stable and might be moving around a lot. So this makes processes like camera matching, which is the process of estimating the camera's parameters from certain features in images, a much harder process, even though it's, you know, not a solved problem under ideal conditions. In our case, it's not, and we really have to manually intervene a lot in that camera matching process, which I'll talk about a little bit in a second. So another thing I want to do with this presentation is go over kind of several principles that might help to guide researchers if you're interested in your work being used at places like forensic architecture. I'm not a geometry researcher per se, although I'll speak a little bit about my research in the future, so I apologize if I use any terminological slippage or anything like that. But I was trying to think on what some things that might be useful for researchers to know if they want their work to be able to be used at places like forensic architecture. So the first principle is this: around that point of low quality footage, develop techniques that are applicable to found low quality footage. And I think this is an important point, not only for us, because, you know, we're a very specific kind of problem domain, but also in the general effort of making geometry research more accessible and more useful to all sorts of folks out there in the world. Lots of people don't have access to high quality footage. And so the developing algorithms and techniques that explicitly work with kind of the sort of footage that you're likely to encounter, online is I think a really important principle, at least for me. In addition to it being useful to us as an organization, I think that there's that kind of ethical undertone, which will be an undertone of this presentation as well, that 3D research is fantastic, but it is often made useful only to those industries and organizations that have the resource to produce it, to produce the high quality images that are required for it, but also to produce the kind of research and techniques and apply those techniques and repurpose papers as engineering projects. So the world of open source 3D and graphics is an incredibly rich and rewarding world, and there's lots of really great work in that world. And I'm pretty strongly of the opinion that we need it as a counterweight to the astonishingly robust corporate monopolies that rival it, such as Adobe and Autodesk. So this next principle is kind of towards that. It's an extension of the idea that papers should come with code. This is really a exhortation further and say, don't only develop your papers with code, but develop your papers into plugins. And this is from direct experience at Forensic Architecture. As a small research agency, we don't have the kind of resource to look into research papers more generally. And that basically limits us. There are plenty of exceptions to this as we code applications like Blender and Unity extensively. We script those applications and write custom things in them often. But generally speaking, the only kinds of research that we can use are those that have ready-to-use plugins in 3D suites like Blender. This is true for us, but it's also true for many other organizations doing public-facing work. And in some cases, I think it's more true for other organizations who maybe don't have the technical capacity that we have, because we do have a small amount of that. We're a small human rights organization, and human rights organizations almost constitutionally, sort of by definition, don't have the time or resource to dive deep into technical literature in a specialized subdomain. And even if we do have that kind of resource or folks who are capable of that, it's usually not in an investigation's interest to sink resource into reproducing the techniques of that sort of literature, as it is usually, or can be, somewhat speculative. Most of our research are architects, and they're comfortable with downloading a Blender add-on from GitHub and testing it, but they might be less equipped to compile code, compile C++ code, debug it, or even something as simple as modifying a Python script or repurposing code that works on your computer to a different environment. In industry, there's often the resource to onboard more experimental research through the layers of technical expertise and deep pockets in terms of both time and money. But for us, the bottom line is that we need a 3D software plugin, basically. Otherwise, we can't use it practically. So this is the second principle. I appreciate that this is probably a harder sell, as it's maybe the case that certain academic venues don't necessarily recognize the extra labor of creating a plugin as legitimate or valuable. And this is, in my view, a problem with the academy. For if the purpose of an academic is to benefit the world, why would we not make every effort as academics to package research in a format where it can be useful to a greater number of people? Plugins would not only make techniques more accessible, but I also think that these plug and play demonstrations would be helpful as teaching and explanatory resources. It's not that hard from our perspective as researchers to write a Blender plugin or something like that. And if the author of the papers don't do it, then they're sort of shunting the task down the line to someone who's probably going to have a much more difficult time writing it. So that's my sort of brief pitch of research principles that I would encourage you all to consider. So in the rest of this presentation, I'm going to do two things. I'm going to talk about our sort of two pipelines at Forensic Architecture that we use, and talk about the problems, or the problem spaces rather, in those pipelines. So one of those pipelines is the 3D fabrication pipeline, which is making those 3D models that you saw in the investigation and making them in a way that has a high enough fidelity for the sort of work that we're trying to do, working with existing tools. And I've broken this down into kind of three major subsections. One is 3D fabrication from a single image video. Another is 3D fabrication from multiple images and videos. And the last is physical simulation, which you didn't see so much of in that investigation that I showed. But I'll talk about an investigation where that was more relevant. In the next part of the talk, provided that I have time, I'll talk a little bit about another pipeline, which is the media discovery pipeline for us, which is how we actually, when we're undertaking investigation, how do we make sure that we find as many images and media artifacts that we can that might be beneficial for that investigation, because we're always working in that public domain. There's always the possibility that there might be another image or another video that we haven't found. And so we have a media discovery pipeline that is more the kind of basis of my work, both at Forensic Architecture and academically, which is about discovering public domain media through image classification and object detection, translating that into a workflow that can work with non-technical researchers, and then some techniques that we use for creating classifiers that can work in our specific investigative cases. So that's fine-tuning with synthetic data. And again, if I have time, I'll talk a little bit about that. So first, let's go back to this investigation, the Port of Beirut, and talk about some of the techniques that were used in this and how it relates to those problem domains. So the first is examining a single video and doing single image 3D reconstruction, which I imagine is a problem that might be familiar to many of you. As I mentioned, because of the low quality of our source images, an end-to-end pipeline is usually not what we want here. We can't just imagine that there will be a single image and we'll be able to perfectly fabricate a 3D model that fits all of the other perspectives. Ideally, we want as many of the intermediate kind of layers to be surfaced as possible. So by layers there, I mean the depth map, the object segmentation, the final geometry layer, the textures, even if that's a part of the reconstructed process. We want all of those to be outputs and also potentially, if possible, there to be an interactive process whereby we can fine tune some of those things when they are wrongly constructed. In the domain that we work in, this kind of domain of low quality images, we expect that the reconstruction process will not work or be insufficient in some way. And so we as researchers need to be able to stop the process of reconstruction at any given point and take what we can from it. Work out that this software or this framework doesn't work so well, but we still want to take something away from that. It can't be an all or nothing approach. And I'll talk about this a little bit more when I get to the structure from motion section. The other problem that we often encounter that you saw in this work was camera matching, which I talked a little bit about before. So camera matching is taking a image or a video and working out what the parameters of the camera are, such that it can fit in the 3D scene that it's viewing, or in the 3D scene that you have. So there are plugins that exist for this, and Blender in particular. There's Perspective Plotter and FSpy. These plugins do camera matching, and they're great plugins. They're open source, they're readily usable, but they suffer from a lack of attention to that first principle that I mentioned, which is that they don't work so well on low res or shaky imagery. Admittedly, it's a slippery slope. You get to a point where the image is so low res and so shaky that it's hard to infer anything from it. But I think there's a case to be made that these plugins are not really expected to work in those low res cases as well. So our process of camera matching at the moment is a fairly manual process as a result of this. It's done in either Blender or After Effects, and it basically consists of bringing in a video, finding some tracking points, which is the process of camera matching generally. Ideally, we automatically find the tracking points, but it often doesn't work, and so we have to debug it often. When we're moving between perspectives, because the video that we have is very shaky, the features can go out of view. There can be aberrations or distortions, and the sort of auto choice of these plugins through contrast often isn't effective for the kind of camera tracking that we're trying to do. And so we have to manually intervene a lot and run the solver partially and then try to make it work again. So this is still from another investigation, which was a reconstruction of a section of land that we did in the Negev Nakab desert. And this is a bird's eye view of a point cloud reconstruction. It's not totally obvious here, but this is a point cloud reconstruction that has been generated through a structure from motion process using a combination of reality capture and Colmap, for those who are familiar with the structure from motion world. So this tends to be a more automatic process for us than camera tracking, but it suffers from that same kind of end-to-end principle. In our work, basically, structure from motion generation of point clouds either works or it doesn't, right? We can run it, and if the videos are of high enough fidelity, or if the algorithm has hit a sweet spot or something like that, then we can generate a point cloud and maybe subsequently a mesh that will be useful for us. But the mode of failure, the success, is basically black or white. It's either good and it's good at like something that we can use and something that we can work with to investigate, or it just doesn't work at all. That might be a nuance of those particular structure from motion implementations as well. I'm not sure. This is not my domain exactly, but this is kind of an invitation to those of you who do work in this domain, that this more interactive process of structure from motion would be something that we would be very interested in. A thing that's related to this is refining an existing model. So the same process of creating a model from an image, but then refining that image from various different perspectives. So you saw in that Beirut investigation, and this is actually still from another investigation, but it gets at the same idea. We sometimes have 2 or 3 or maybe more video captures of an event from different perspectives. And we want to create a 3D model, and then refine it from those various different perspectives, probably incrementally and probably with a human in the loop. We don't want this kind of automated end-to-end process again. We want to watch it, as it were, and see that it works effectively. So again, because there's interactivity involved, this kind of emphasis on interactivity feeds into that second principle that I talked about, which is turn your work into plugins, because plugins are a better space where that kind of interactivity can be used and made use of by folks who are not necessarily technical researchers in a computer scientific sense. And you can, it's really interesting. It can be really interesting to work with those folks who are actually using this in the real world context through that kind of interface of the plugin. What sorts of things might they need in order to make your technique useful for their work? That can be a really gratifying and rewarding experience. So this is as much a workflow problem as a technical one, I think. I'm conscious of time, so I'm probably not going to get to the last part, which is talking more about the 3D generation pipeline. The media discovery pipeline, but I think I will have enough time to finish all of these different sections. So this next problem is one of synchronizing multiple videos. So this is a related problem. We have multiple different videos. This is emphasized by the timeline at the bottom here, where we are looking to take all of this found footage and plot them into a map or into a timeline where we know when those videos were filmed, so that we can start making forensic claims on the basis of them. We've looked very briefly, and there's some posts on our website about this if you're interested, at trying to synchronize videos on the basis of sound, because that can sometimes be an effective way to do this algorithmically, especially if the video is shaky and there are kind of loud events in the video. But we don't have a kind of ready-made process for this. And so this is, again, another invitation to those of you interested in this. This would be something that would be really useful, not just for us, but for many other human rights organizations as well, who have the same kind of problem. Another problem space, and one of the last ones that I think I'll get to in this presentation, is this idea of physics simulation in certain investigations. So as I mentioned, it wasn't seen so much in the Beirut investigation, but this was an example from an investigation that we did at a protest, documenting a protest in Chile, and the amount of tear gas that was used at this protest. We did some volumetric simulations to work out what the density of tear gas particulates would be over the course of the day or the afternoon where this was taking place. And the simulation of this is what helped us to make a claim about the average CS there meaning tear gas, the average CS concentration in time in various spaces around the plaza, and the way that it drifted into surrounding areas and infected waterways that carried it out in other places. So this is really part of a lot of, or a sub-thread, if you will, of our research, which is really focused around tear gas and the way that it's used in domestic contexts. So this was where I was going to move on to the third section of the talk, which was the media discovery pipeline, but I'm conscious that I've probably hit time. Is that the right assumption?
I think we can have a few minutes to go on. But okay, it's up to you, yeah.
Sure. Let me run through this really quickly, then, as quickly as I can. So another sort of problem that we have, which was hinted at in that Beirut investigation, was where to start, right? Where do we start with these investigations? Often we're directed to a particular context, and we have a way of finding sort of key elements of the imagery, because often we're directed to that context because there are images or video of it. But then there was always the question of what other images or videos could there be? So the investigation that I want to just really rush through here was one in which we were looking for evidence of military presence in Eastern Ukraine at a time in 2014, where the military presence was fairly obvious because there was a lot of military vehicles, and in particular, there was this one type of tank, the T-72B3, which was manufactured in Russia and hadn't been exported anywhere, and so it was a pretty clear symbol of Russian military presence in Eastern Ukraine at that time. There was many videos of this, and some other groups had already done a lot of very good previous work, such as a group called Bellingcat, who we work with often, documenting these videos and how evident it was from all of these videos that there was Russian military presence in Eastern Ukraine at this time. And so what we sought to do was kind of systematize all this evidence and put it into an interactive map. One thing that we also developed during this was the speculative approach of trying to find more images through object detection and image classification algorithms. And so we developed this kind of pipeline, sorry, skip through it there, where you can choose an object classifier and then apply it on a media space or a media domain, which would be like a YouTube set of YouTube search queries and a time maybe. And then that would run somewhere, and then it would provide you with an interface like this, where each cell here represents a video that exists on a platform like YouTube. From left to right is the timeline of that video, and the redness in this footer here are the positive frames as determined by whatever algorithm you ran. The brighter the frame, the higher probability of the classification. And then you could rank this by various different metrics. So this is a kind of interactive way to search to leverage object detection and image classification algorithms to help with the discovery of material that might otherwise not be discovered. And we found several videos that even after several months of specialized Eastern European researchers who were specialized in that context, looking online, we found several videos through this approach that we wouldn't have found otherwise. And this is where it all went. We developed this platform that's an interactive cartographic platform that shows all of these events and has links to the original source material. I just want to emphasize that this platform is all kind of public as well in this open source kind of mode. So the data for this platform is basically just a Google Sheet. And this is another thing that I think is really important to emphasize, is that there's no point in reinventing the wheel. Many people are familiar with Google Sheets, and using this as a database is a perfectly acceptable thing for the scale of the data that we're working with here. And we generalized the frameworks that we used in this investigation. So this time map here is the interactive cartographic platform that you saw before, and this has been used in several investigations since, including a recent one that we collaborated with Bellingcat to do in the Ukrainian context, the Russian-Ukrainian context. And there were the associated sort of toolings that we used as well, which we made open source. So mTriage is the framework that we use to orchestrate and download that media and apply classifiers over it. I think I should probably stop there. There's a brief couple of pictures here about how we then tried to fine-tune classifiers using synthetic data that we were able to generate through a Unity engine. But I will just skip through that. And if you're interested, I encourage you to look at these papers and look at the information on our website.
Sounds good. Thank you, Lachlan, for the fascinating talk. It's definitely, and also your insights into like how to make the more technical line of research useful for this very meaningful and important area of application. So now we will kind of start a joint Q&A session for both of our speakers. And in the meantime, please continue to post questions in the YouTube chat. And if you still have questions left afterwards, please use our Discord channel for offline discussion. And I think I'm gonna kind of like ping pong questions between the two speakers so that like each of you have time to rest. And I will start with a question for Congyue on the vector neuron. This might be a stretcher question, but it's also kind of me being curious about. So like we know like positional vectors are probably like the most common form of vectors in geometry processing, or like in the area of like graphics and vision. I guess in the area of vision, have you kind of thought about the implications of vector neuron for other vector data, such as like RGB color quantities? If that.
That's a very good question. Especially like RGB, like or more generally like scalar features on point clouds is also like widely exists in a lot of tasks. Like actually, there have been a lot of people asking me about like, can you deal with RGB data? Because that we actually have a follow-up work like extending the operators, also like including the scalar features into the network. Well, like, should I talk more about that, or I don't know?
No, it's totally okay. But yeah, it sounds really definitely cool. You have a follow-up work on that. We'll like definitely look forward to that.
But in general, the idea is that like to build more communications between the vector features and the scalar features to like, I mean, of course, like you can also process the kind of data separately, like just like have different layers and like stack them together at the very end. But like that's, I mean, I feel that's what like you're really looking forward to, but more like you want some communications between them.
Yeah, that sounds really cool. Another question is that have you considered to also further extend your approach to be like scaling equivariant instead of just like rotation equivariant?
Oh, that's also a very good question. But I feel in general, I'm not thinking very deep into this as a separate task. Like I might think about it like in some specific applications, but like also I feel the definition of the scaling might be a little bit ambiguous. Actually, beforehand, I was also thinking about translation equivariance, but for partial shapes. I feel like both for translations on partial shapes and for like scaling, I feel the difficulty is not only in the representation or the construction of the network, but also in say like how do you define a canonical scale or like canonical translation for those kind of shapes. I feel that's also something maybe task dependent.
That makes sense. Thank you for the answers. Here is a question for Lachlan. You mentioned like about like some kind of research about like using audios to also kind of augment this line of research. We are curious, where can we find more about like synchronizing videos based on sound?
Yeah, so as I mentioned, we have a very sort of small amount of materials on this online. If you go to the forensic architecture and then go to the open source software page, there is a blog post called Detecting Tear Gas Canisters, which I can also link in the chat for those who are interested, which has an end section, which is about some brief experiments in this. It's more an idea than anything, and if you're interested in potentially working on that and working in forensic architecture's case specifically, I'd be more than happy to talk with folks who are interested in that. So feel free to send me an email or get in contact with me any other way.
Okay, sounds good. Another question for you is that so all of the for example, I think one of the examples you show like a lot of bags kind of stacking together in a warehouse. Are those bags like manually modeled?
Yeah, so this is an important point, is that most of the sort of geometric forms that you see in our investigations are manually modeled. We would love to automate it, and it would really save us a lot of time. And there are various points in the process in the 3D fabrication pipeline where we automate certain parts of it. But generally speaking, they're all manually modeled as opposed to automatically modeled.
Yeah, so we can like notice that in your presentations that it seems like you do have like this line of research in forensic architecture have this like a preference for like very clean geometry in your like presentation in the videos or like whatever footage you are preparing. But like I think there's like this popular line of research in computer vision right now. I don't know if you're familiar with this called NERF, where like people do visual synthesis. They kind of just synthesize the appearance into synthesizing the geometry. So I guess like in your area of research in forensic architecture, do you think it's better to do like pure geometry reconstruction? Like would like appearance reconstruction also come handy in your?
Yeah, so appearance reconstruction will come in handy as well, because these are all basically the reason that we want to reconstruct this geometry is not because we need it in a particular format, but because we want to try to do some analysis from it. And so that analysis might require very kind of like pristine geometric forms that exactly match it. It may not. It may just require a general kind of depth map of a larger scene from which we can then make conclusions about how far something must have traveled or something along those lines. And so the short answer is yes, we're still interested in all those forms of geometric reconstruction, even if you didn't explicitly see them in that investigation or in other investigations, really.
That makes sense. I guess kind of along this line of questions, I have one more question for you, is that it seems like realism is kind of very important for like doing like documentary journalism, like reconstruction. And you show some footages of the smoke simulations. And we're just kind of wondering, how do you guys approach like applying the constraints through the video to reconstruct the smoke? Because like probably because of my limited experience with like smoke simulation, we kind of always start with like a very curated starting point, and then like we do the smoke. Yeah. So kind of just wondering, how do you like kind of apply that constraint to like a very graphic simulation sort of practice?
Yeah, again, the answer is with a lot of manual intervention. It would be great if there were a way to do a smoke simulation or something like that, where you could give it the constraint of so many frames of the video and say, I want you to work out how much smoke you need to start and what the wing conditions should be in order to perfectly match the pixels that are identifiable in this image, even if we had to like manually mark those pixels ourselves. But to our knowledge, that kind of way of starting a simulation doesn't exist. And so it's a lot of trial and error of trying to do a smoke simulation that matches the pixels in the video to a great enough extent that we can be confident that we can make some sort of analytic claim about where that smoke must have traveled afterwards, or some other sort of relevant tidbit. Yeah, we don't have a silver bullet for doing those kind of simulations, but if you have one, please let me know.
Yeah, we'll definitely keep an eye out for that. So another question that's for Congyue. Yeah, so your work kind of like try to construct this framework for like rotation independence in some sense. Like, have you thought about like in some cases people will actually want rotation dependence? Like, for example, I have like a consistent up direction, or like you have a prior distribution on like the orientation of the models. Does like vector neural actually make this harder or like easier, or like?
Oh, actually, I think this is a very good question. Because in the paper, we also noticed that in some papers dealing with rotations, like they only do augmentation along the z-axis, which assuming that you know the up direction of the road and all objects are placing on the floor, and like you can just like rotate it like around the z-axis. And currently, vector neuron isn't able to deal with that. Like we are also very interested in like how this area can be tackled in the future, but like at the current stage, I don't have a clear answer to this. But I have to say, like, this is a very interesting direction and very useful for a lot of applications.
That makes sense. Well, thank you both for the great answers. Yeah, we're almost kind of out of time, so we'll kind of have to stop here. And for people with more questions, please feel free to take them offline our Discord channel. And thanks everyone for joining this colloquium. And let's thank our speakers again for this very interesting session. And we also want to thank our artist, Yuharu, for making the amazing poster for this week. And see you all next week.